Hello, we are delighted to welcome you to our presentation featuring UVC Disinfection Drones. Meet my talented team of colleagues, Nada, Khatija, Salama, and myself, Farah. This is the agenda for our presentation. The COVID-19 pandemic has impacted all of our lives, requiring us to take extra precautious measures. It requires people's attentiveness and wariness, along with extensive sterilization and disinfection of public areas. However, frequent sanitization of our surroundings is a difficult task to perform thoroughly and repeatedly, and hence requires a solution to it. Recently, unmanned aerial vehicles UAVs or drones have gained a high rise in popularity to solve sanitization issue and to perform various tasks. They can take charge of frequent sterilization of accessible areas at regular intervals with high efficiency and less labor. Technology advancements have proved that innovation has no limits and essential activities can be easily automated. As engineers, we are obliged to propose efficient, optimal, and autonomous solutions to solve practical problems. Moreover, the pandemic has escalated the need for contactless solutions with less or no human intervention. We provide a modern sanitization solution to frequently accessed locations using unmanned aerial vehicles, UAVs, or drones. Our project must follow the constraints of the lab environment where various equipments and components may pose as obstacles while following proper disinfection and sanitization methods. Such a difficult task requires drones or unmanned aerial vehicles that precisely navigate through and sterilize indoor lab environments in fixed schedules to carefully maneuver around cluttered environments.
Background and literature review. Subsystems to tackle problems. We have 4 subsystems that will help us to tackle the problem at hand. First up is the navigation. It requires both precision and accuracy as well as computational complexity. Next is the flight time, which requires autonomous charging for the flight. Next is the flight control, which requires precision and API over GPS. Next is the use case, which requires both efficiency and need. Navigation on drone systems. Navigation based on onboard localization of the drone. We have the indoor GPS and the vision-based approach. For the indoor GPS, it's indoor real-time location systems used for navigation and tracking, while the vision-based approach is navigation based on the visual feedback of an optical sensor, which is either mounted or built-in on the board. Navigation on drone systems. For the vision-based approach, we have the VIO and the VSLAM. The VIO is the navigation based on visual and combined IMU sensor readings, while the VSLAM is simultaneous localization and mapping of an unknown environment based on visual input from an optical sensor. For the indoor GPS, we have the Marvel Mind, which is an indoor navigation and tracking system based on stationary ultrasonic beacons. Comparing all 3 systems, we have decided between the VSLAM and the Marble Mind. We have chosen VSLAM over Marble Mind because of its precision and because it is more cost efficient.
So these are the various flight controller options that we are considering. We are considering to use model AI PX4, which can be paired with Voxel Flight Tech, and it is also compatible with our development drone, which is the Voxel M500.
Since the drone requires charging every 20 to 30 minutes, an autonomous charging station is required. We have 3 solutions. First is the robotic arm, which is a wired power transfer using robotic arm with electromagnets and the camera for detecting a certain battery type, while the WPT is an oriented landing or non-oriented landing charging station that uses wireless power transfer. And the third is an existing product, which is a charging pad. The disinfection method that we have chosen is UVC, and its advantages are as follows. Its surface disinfection is more sustainable and eco-friendly and has a higher effectiveness in inactivating viruses. The LED UVC emits the best wavelength to sterilize against COVID-19, and its compatibility. Solutions that can be carried on board and has a low power consumption and is highly efficient. There are 3 possible solutions for the LED PCB, which is the strips, rigid PCBs, and UVC LED array. For the UVC placements, our initial design was placing the rigid PCBs between the arms, but due to the drone payload, this idea would not work. Thus, we have chosen the UVC LED matrix, where we will place it underneath the middle of the drone.
This diagram represents a system overview. There is an admin portal which is used to plan and schedule disinfection sessions based on a floor and detailed map. The drone navigates autonomously using VSLAM by means of a tracking camera. The location data is then used to create the signal request, which is to be sent to the flight core for flight control. Visual feedback created from VSLAM is accessible on the admin's portal for remote control. We also have an acoustic model running in parallel that will capture environment noise to detect the presence of people in the lab to stop the session for safety. Once the drone detects the barcodes on the benches, the UVC LED matrix is turned on for the specific time depending on the PCB while maintaining an altitude of 20 centimeters throughout. The progress is continuously updated in the admin's portal dashboard section. Finally, when the session is over, the drone goes back to the charging station, which is a robotic arm with electromagnets to be connected to the battery of the drone for charging. A camera is used to detect and segment a tag on the battery so that it could move the robotic arm to connect to the drone. The Voxel M500 is the development drone that we are utilizing for this project. It is equipped with stereo, tracking, and 4K FPV sensors. Other specifications are mentioned in this table. In this section, we'll be presenting the experimental results of our project. For the acoustic approach, we first implemented a Simulink sound separation model with a panning source subsystem to localize drones based on sound inputs received. The mixed and separated audio signals are plotted in the time domain as shown in these two figures. But despite producing good results, we conclude that it is an inefficient technique because the model requires us to supply separate audios and the model will mix it prior to separations, which is not quite practical in a real-life scenario. So this takes us to the next approach which we adopted using Google Creative Labs teachable machines, which will train a custom model and detect in real time human speech signals in the environment where a drone is operating. The model has three classes, namely the background noise for capturing white noise with 40 audio samples used for training, drone class with 28 audio samples of different intensity propeller sounds of drones, and humans class with 20 audio samples of human speeches with varying voice modulations. These are the samples from our testing. We have set the overlap factor to be 0.5 to clearly be able to distinguish a drone and a human sound. In case 1, the disinfection session is not yet activated, so the labeling is on the background noise, which has a confidence score of 99%. In case 2, we simulate a scenario where the session is active but there is no human intervention. Hence, the confidence level of the drone sound is shown to be 100%. And in case 3, there is a scenario where a human is far by and he's approaching the premises such as the lab where the session is taking place. As the voice is very faint, the confidence score of the human speech signal is just 20%, but the system raises alert to stop the operation. In case 4, the session is activated and there is also a human inside the room, owing to the majority in the confidence score, which is 59%. System must come to an emergency halt for safety reasons, demonstrating the successful working of the model. This is a mini simulation of the disinfection session carried out in one of our computer labs in university.
Our solution is also accompanied with an admin's portal, which is a cross-platform application in which the user can plan and schedule the disinfection sessions using the calendar tab. In this calendar tab, they can select the date and time as well as the room they want to schedule a session for. And then we have the dashboard tab, which is where the user can view the current room undergoing disinfection. It displays the room layout and shows the progress and status of the disinfection process. And by scanning the QR code, the disinfection status is updated along with the progress status. The user is able to track the drone's battery as well as the remote control to be able to receive visual feedback due to the depth estimation from stereo video. On the remote control, they are able to control both the speed and the direction of the drone. Here are two examples of the admin portal's dashboard. As you can see on the left, we have the status report shown. It is generated and shows that the session is completed successfully, while on the right, we have the session has been stopped. It shows an emergency alert that the scheduled disinfection session is halted due to the presence of humans in the premises. And next, an alert and cause are shown to the user. The alert says that the emergency stop is in action and that the cause is human intervention. The simulation of the drone navigation has been done using Q-ground control, which is due to the current circumstances in which we are unable to fly the drone. The software will work along with the PX4 powered UAVs. The drone flight path is mapped using the software and the simulation of the flight is generated. To conclude, our project aims to provide time-efficient and effective disinfection and sterilization methods of target areas as a means of aiding and reducing the spread of the COVID-19 virus. Our solution will conduct sessions within a given time frame where the drone will be deployed to disinfect and sterilize the classrooms, laboratories, and other areas. The drone's motion and disinfection path are tracked and mapped onto the application. The application allows tracking, scheduling, monitoring of the performance, and session settings. On behalf of my group and I would like to thank you for watching our presentation.